This algorithm uses the concept of a two-pointer traversal, which we've already used before. The key difference in this algorithm is that the pointers are both traversing at two different speeds. And so we have the Tortoise, which is the slow pointer, and we have the Hare, which is the fast pointer. Specifically, the fast pointer is traversing twice as fast as the slow pointer. So if the Tortoise is traveling a distance of a plus b, then the Hare will travel a distance of 2 times a plus b, or 2a plus 2b. So before we continue, we're just going to go over a very simple example. Okay, so the first problem we're going to go over is finding the middle of a linked list. I'm not going to write the code because it's mostly self-explanatory. Essentially, we want to find the middle element of a linked list. And so normally this would just require 2 iterations, one to find the length of the linked list, and then the second iteration to go through halfway. With fast and slow, we can do this in just 1 iteration. And so the key thing here is, if we have a pointer that reaches the end of the linked list, and it has traveled a distance of 2d, our slow pointer would have traveled a distance half of that, which would be exactly halfway through the linked list. And so the way we do this is we declare 2 pointers that start at the root node, and we keep traversing until Hare equals to null, which means it's reached the last node, it's gone past the last node. And so our slow pointer we just traverse as normally, as you do through a linked list, and for our fast pointer we traverse twice as fast. So we're not just moving on to the next pointer, but we're moving on to the next one after that. And once this reaches the end, we want to output the one in the middle, which is our slow pointer. So we return the value at taught. And just to show that this works, if we have this example here, and this is just a manual construction of a linked list, you'll find that the middle node is this one here, 5, as we have 4 items in front and behind of it. So if we execute this, we get 5, as you can see. But the problem that I really want to go over is this one, the duplicate number problem, where essentially we have an array or a linked list, and the question is simply asking us to find the duplicate number. And we could also just solve this problem by using a hash map or any type of map type data structure. However, one of the requirements for this problem is that we want to solve it in constant space of 1. Imagine that we have a racetrack, and we have our slow pointer, which travels a distance d, and our fast pointer that travels a distance 2 of d. In this case, our slow pointer has travelled halfway through the racetrack, and our fast pointer, since it travels twice the distance, will make a full lap around. Now what we want to know here is, when will these 2 pointers meet up with each other again? Since at some point, the fast pointer will have to lap around until it reaches the slow pointer again. And so, if our slow pointer travels the full distance around, our fast pointer will travel twice the distance around, and it'll be at this exact point that they both collide. And notice how the root node, or the starting point, is within the loop. And so this isn't particularly useful for the problem we're trying to describe. And the reason is because we are going to have something like this instead. So here we have the same case. So the only difference is the root node doesn't actually start within the loop, it starts before it. Once it enters the loop, that's when the cycle begins. Just like before, we have a collision point, and because this problem becomes slightly more difficult, it's better off that we start labeling certain areas. So we label A as the distance from the root to the start of the loop, distance B from the start of the loop to the collision, and then distance C, which is the collision to the start of the loop. The reason why this is important is because we want to ask, what is the distance that the slow pointer is traveling? Starts at the root, it takes distance A, and then it takes distance B. In case of the fast pointer, it takes distance A, B, C, and then back to B again. Now we can do a bit of simplification here. We have 2D equals A plus 2B plus C. And since we know what D is, we can just substitute A plus B, and we have 2A plus 2B equals A plus 2B plus C. And when we simplify, we see something interesting. We see that A equals C. So this means that the distance from the root node to the start of the loop is equal to the distance from the collision to the start of the loop. And this is very important to us, because what we can do now is we can set our 2 pointers, the Tortoise and Hare. The only difference is the fast pointer is not travelling twice as fast this time. They are both travelling at the same speed. And why this is important is because if they're both starting at two distances equally away from the center, which is the start of the loop, if they both traverse at the same rate, what we'll find is they will both meet at the start of the loop. And this is precisely how we solve the problem. So just as a summary, this is a two-step solution: finding the collision point, and then the second step is finding the start of the loop. This is the location of the duplicate number in the linked list, hence why a loop starts in the first place. But before we continue, there's one final thing that we need to go over. When I place slow at the root node and the hare at the collision, the problem is the tortoise is one step closer to the start of the loop, whereas the hare is one step behind. And so there's two things we can do here. Either we can move the tortoise backwards, or we can move the hare forwards. And so an alternate solution is to rewrite the data structure so that we have this terminal node at the beginning that doesn't represent any value. And so this places both the tortoise and hare at equal distance. An easier solution without messing around with the data structure is we just push the hare one step forward, and that's exactly what we'll do. Okay, so now that we're back to the code, there's two ways of doing this. Either we can do it with a standard array, or we can do it with a linked list. I'm going to do it with the linked list just because of that extra edge case at the end. However, I do want you to try and do it with the array by yourself as well. So the first thing we do with these problems is we define our 2 pointers. So we have our tort, which is equal to head, hare that is equal to head. And just like we did before, we want to keep iterating until our hare does not equal to null pointer. And we also want to make sure that hare next doesn't equal to null pointer either. And this is mainly just so that we don't run into a null pointer exception. And you only need to check the hare because the hare is always ahead of the tortoise. Similarly to what we did before, we just do tort equals tort next. Next. And where we want to stop is if these two values are pointing to the same memory address. And if this is the case, so here's the thing: if this was a Boolean question, whether there's a loop or not, we would just simply do return true. Alright, but you want to know what the value itself is. So instead we break out. And likewise, you could also just do return false here. Okay, so remember, now that we found where the collision is, now we want to find what the start of the loop is. So like I said, to find the start of the loop, the distance A and C are equal to each other. Well, we declare our tortoise to start at the head again. Our hare, normally you'd leave the hare alone, but like we said, it needs to be one step ahead so that the distance is the same. So we're actually doing hare equals hare next. And then we want to traverse them both at the same speed now. So while these don't equal to each other, we want to just want to traverse them both at the same rate. Okay. And when they do equal to each other, then we finally have our value. So we can just output our val like that. Okay. And that should be it. Yeah, so in this case, our duplicate number should be 5. So we have 2 5s here. Okay, so yeah, the reason why I was outputting 1 is because the slow and fast pointer were both at the root node, which was 1. So instead I just created 2 different pointers, but it's still the same thing. And so when we output this now, we get 5, just like we wanted. And the code for this is pretty much the same for a standard C++ array. The only difference is this part here. You don't have to worry about pushing the pointer one step ahead, because in an array you're not indexing the 0th element, because the array only contains values from 1 to n, and so you can treat 0 as your terminal node. But moving on, The last problem we're going to go over is it's called the happy numbers problem, and this one's different because it doesn't involve a C++ array or a linked list. Instead, we're dealing with a sequence, a mathematical sequence, and this shows how cycle detections aren't necessarily restricted to just list type data structures. And so this is simple. A happy number is just a number where if you sum up the squares of every digit in the number, eventually it leads to 1. For an example, if you have the number 129, we're doing 1 squared plus 2 squared plus 9 squared, which just simplifies to 86. And then what we do is we repeat that process again. As we know, this converges down to 1. So 129 is a happy number. So as you can imagine, we can have a loop here if the same number appears twice. So to demonstrate this, imagine we start with the number 12. It's only up till we get to the point of the number 89 where our loop starts. And it's at this point here where we meet 89 again. And so it's this section over here that is our cycle, our loop. This is fundamentally the same as the previous problem. And the only difference is we're taking in a number this time. And our 2 pointers are just standard variables that point to n. Okay, so once we define this, we start our loop. And the condition here is, well, we don't actually need a condition because we're not dealing with pointers, so we don't have to worry about null pointer exceptions. So instead we just do our standard while true infinite loop until we get the condition that we want. If you remember, when we have a number, we want to calculate the sum of squares. So we can either do it here, or we can just define a function up here called sum of squares. And we take in our int n. And note that this also works for n equals 1, because 1 times 1 equals 1. So this function is our way of saying tor to next or tor to next like we did previously. The only difference is we're doing a equals sum of squares a, and b equals sum of squares, and in this case we're just calling it twice, b. Both of these equal to each other, and this is where we want to break. Okay, and it's a cycle, or they are both 1. By cycle I mean start of loop. So if we're in a cycle, then we want to return false, but if they're both 1, then we want to return true. So the simplest way to do this is just return a equals 1. Oh, my bad. No. Okay, seems like we have an infinite loop for some reason. Oh, this should be divide equals 10. We're trying to cut off. Moment of truth. And there we go, we get true and false, or 1 or 0. In C++ it's the same thing. So yeah, that is the fast and slow pointer technique. There are more interesting things you could do with this problem. I'll probably make a part 2 of this and go over some more interesting problems. So yeah, I hope you enjoyed this video. I'll be covering more algorithm videos in the future. I want to make more, so stay tuned for more videos and leave a comment for anything else you want to see. And yeah, thanks for watching.